We're going to be moving on to a new unit called chemical equilibrium, and we're going to start this off by looking at a very quick simulation. So what I want you to do is actually pause this video. You see this link right here? I want you to type it in before we move on. Did you type it in yet? Okay, let's begin. At the very front home page, you're going to be introduced. So I'm going to read real quick the introduction and tell you what's going on. Introduction. On the Kinetics tab, the simulation models the time dependence of a one-way reaction. The rate constant, percent of A converted to B, can be changed to see how this affects the behavior over time. On the Equilibrium tab, not only does A convert to B, but now B converts to A as well. The rate constants of both reactions can be changed to observe how the rate constants affect the equilibrium amounts and the rate at which equilibrium is approached. We recommend to start with the kinetic simulation, then equilibrium, and then Le Chatelier. Click on the kinetics button or tab to begin. So we're going to start with the kinetic simulation, and for this one it's a one-way reaction. What it says right here for chemical kinetics is the amount of A changes over time as A is converted to B. To see how the amounts of A and B change over time, select the rate of conversion, the percentage of A that converts to B, then type in the numbers of A that convert to B at each step. So it's a little bit confusing, but you're actually going to go right here where it says A goes to B, A converting to B. Underneath there's a drop down box. Now these are percentages, and they didn't put the percent sign there, so that's why it's a little bit confusing. So I'm going to choose something easy, like 50. You choose something else. And then after I kind of get you started with this, you can go ahead and try it on your tab. So what we're doing here is we're actually starting off with, according to this table, we're starting with molecules of A. These are reactants. And right now there is no molecules of B. There's 0. But there is 100 molecules of A. Okay, just to keep the simulation very comprehensible. What's going to happen is A is going to convert to B, and at the percentage that we set it to. So mine is 50%, meaning at the first step, 50% of 100 molecules is going to convert to B, to our product. So what is 50% of 100? You probably already know it. But what we're going to do is, I'm just going to show you on a calculator. You type in 100 and then you multiply it by 50%, which is times 0.50. Okay? So it turns out to be 50. Were you right? So I'm going to type in 50 right here. This column is telling me how much is converted for that step. 50 molecules convert. So what it's showing you now is underneath column A, you started with 100, but 50 of them is converted. That's what we calculated. Now there should be 50 remaining. And in column B, you started with 0, but then 50 of them were converted to B. Now you have 50 of B. This is after step 1, okay? And then you keep going. So step 2, I'm going to do step 2, and then I'm going to stop. So step 2, now I have 50 molecules of A. 50% of that amount is, let's see, 50 times 0.5 is 25. So you probably would have already known that. Half of 50 is 25. So 25 molecules now convert to product. And what's going to happen is if 25 of them convert to product, then there's going to be 25 left of molecule A. And if there's now 25 more product, 50 plus 25 is 75. All right. On the right-hand side, you may have noticed that there is a line graph. This line graph is just keeping track of how much molecules of A and molecules of B you have over time. So for example, at the very beginning, time 0, you had 100 molecules of A. And at the beginning, time 0, you had 0 molecules of B. So this is just showing you over time what's happening with your molecule of A and your molecule of B. A was decreasing and B was increasing. On the bottom you have this nice little simulation of like how much of each molecule there is at this current step. So at this current step, there's 25 molecules of A, 75 molecules of B, and that's why it looks like there's more blue molecules. All right. So this is a really good simulation. I'm going to stop at this moment, but I want you to continue going to do this calculation with your calculator until you reach a point where it seems like you've stopped. Once you have reached that point, you can go ahead and try the equilibrium tab, which is what I'm going to be doing right now. So pause the video, try the kinetics one first. Once you're done, you can go on with the equilibrium one. Alright, now we're at the equilibrium simulation. I'm just going to go ahead and read that little blurb real quick. Not only can A convert to B, but B can also convert back to A. To see how both A and B change over time, select the rate of conversion or percentage of A to B and of B to A. Then type the numbers of A that convert to B and B that convert to A into each step. Okay, so basically an equilibrium reaction is actually what we call reversible. It can go backwards and forwards. And what we need to do here is for these two drop-down boxes, we select the percentage of what is converting forward and what is converting in the reverse direction. So I'm going to choose for A to B to be 25%, and for the backwards reaction, B to A to be 50%. And I want you to choose something different to see how your numbers are going to be different compared to mine and how they're going to be similar. So we're going to do the same thing here. Now, we're starting off with 100 molecules of A and 0 molecules of B, but 25% of this 100 is going to convert to B, to our product. So we're going to take 100, we're going to multiply it by 25%. Oh, it's 25, duh. Okay, so 25 molecules of A converts to B. Now I have to go ahead and do the reverse conversion. We're starting with 0 molecules of B, and 50% of 0 is going to convert to A. Well, if you don't have any B, you can't convert any of it to A. So 50% of 0 is going to be 0. So after this, let's see. We're going to end up with 75% or 75 molecules rather of A and 25 molecules of B. And then we're going to continue doing this. So now we have 75 molecules of A. We want to get 25% of this and convert it to B. So 75 times 0.25 is equal to 18.75. And since it's above 0.5, I'm going to round this number up to 19, because technically you can't have like 3/4 of a molecule converted. That just doesn't make any sense. So 19 molecules, I'm going to round up. Now for B, we do have 25 molecules of B, as indicated right here. Now 50% of this 25 molecules is going to convert back to A in the reverse direction, because equilibrium reactions are reversible. So we're going to start with 25 times 0.50 to get 50%. Okay, 12.5. Since it's 0.5, I'm going to round this number up to 13. So 13 of these 25 molecules are going to convert back to A. And those are our numbers that we're going to get. And then we keep doing this until we reach a point where we think we're going to stop. Okay, it'll show you at what point you're going to stop. So I want you to try this simulation and then reach that point. So pause the video, and then once you have reached that point, I want you to go ahead and compare between the one-way conversion and the two-way conversion. Okay, so the kinetics is the one-way, the equilibrium is the two-way because it is forward and reverse. And then see what big ideas that you can draw from this by looking at the graphs and looking at your data table. So pause the video and try to finish this simulation, please. Alright, hopefully you finished both simulations. Now I'm going to go ahead and talk you through just the big ideas that you can get from each of these simulations. Now here's the kinetics one, the one that is one direction to create only products. Now what you should notice is that all of your reactants are going to be depleted, basically. You start with 100 of your molecules of A, but then eventually you're going to get pretty much 0 molecules of A. And that's because all of them turn into product. So you're going to get pretty much 100% product if you follow this graph. And this is what we call a reaction going to completion. It makes only product, and you can kind of see this in the simulation. There's only blue molecules floating around here. So it's kind of that simple. And depending on what percentage you put in this drop-down box, if you have a higher percent, then that means it's going to go to completion faster. It's not going to take this many steps. It's going to take fewer steps. If you have a lower percentage, then it's going to take longer. You're going to have probably more steps than I have right here. As for the equilibrium simulation, this is the data that I got. So what we should notice from the graph is that, okay, you start with 100 molecules of A, and then you get to a point where it doesn't change anymore. This is 67 molecules right here, because I'm looking at my data table. So you start with 100, but then you end up at 67, but it stays at 67. And then for molecule B, you start at 0 molecules of B, but then you increase it, and then it kind of stays the same. It plateaus off. It's going to be 33 molecules, because according to the data table, that's how much we have right here. 33 molecules is how much we end up with. So if you were to continue this calculation, you're probably going to notice that it's going to just stay the same. We can actually keep going. The data table is endless. And it's not going to change because of the amounts that we have, the crazy math that's going on here. 25% of 67 is going to be 17, and then 50% of 33 is going to be 17. The rate of the forward reaction is basically going to be the rate of the reverse reaction, so there's going to be no change. This is what equilibrium is. If the rate of the forward reaction is equal to the rate of the reverse reaction, there is going to be no more change. And the big thing that you should get from this is, if you take a look at the simulation right here, the reaction has not gone to completion. We still have our red reactant molecules, even though this reaction seems to have finished. And I'm air quoting finished because the reaction really doesn't finish. It keeps going. 17 molecules of A converts to B, and 17 molecules of B convert back to A. And it continues like this forever. It technically doesn't stop, and this is what we call dynamic equilibrium. All equilibrium reactions, at least as applied to chemical reactions, they actually do not stop. They continue going. It just seems like it stopped. It's because there's no net change. The rate of the forward reaction equals the rate of the reverse reaction. So hopefully you kind of picked up on this big idea between the kinetic simulation and the equilibrium simulation.